Hi everyone, welcome to our fifth lecture for CSC 110. This lecture is going to be on binary logic and binary circuits, and it's the culmination of the lectures that we've been doing up to this point. So let me just remind you what we've done in the course up to this point. We started off with this idea of technological revolutions and said, humanity went through various technological revolutions where new technologies entered our society and really changed us. Okay, we're undergoing a technological revolution right now. Okay, and it's going to have serious repercussions on our society. And that technological revolution, you could call it the digital age or the information age or whatever, but it's basically being driven by the fact that we have invented what we call mechanical minds. Okay, so in the past we had different things that we made mechanical, like mechanical muscles, but now we've gone one step further and we've made these mechanical minds. And I promised you that I would eventually get to the point where I would be able to design for you and show how a mechanical mind could be built, just like the way a computer works. Okay, and that's this lecture. So this lecture is going to kind of end that series. I have to tell you, this is going to be by far the hardest lecture. Okay, now I understand, that your majors aren't in the hard sciences or whatever, but nonetheless, I think it's a very good thing once in life to see how digital machinery works. Okay, and it's not just for the sake of seeing that so that you have some edification in your education. It's going to have some practical purposes later in the course. Okay, so I'm doing two things at once. I'm sort of getting at the essence of what digital technology is, and at the same time I'm also preparing things that we're going to be using later in the course. Okay, so yes, it's going to seem like a very difficult lecture, but at the same time it's going to pay off in the rest of the course. And you won't find the rest of the course as difficult as this one. So I'm warning you up front. But nonetheless, let's start. Okay. So binary logic and binary circuits. What is that? Okay. So first, binary logic is it's just an abstract operation that you can do with the human mind. It was discovered by a fellow called George Boole. So it's sometimes called Boolean logic instead of binary logic. But it's just like arithmetic. But in arithmetic, what do? You add things, you add numbers, you subtract numbers, you multiply numbers, you divide numbers. Here, instead of using those operators, you use logical operators. And the ones that we're going to study is and, okay? And it's just like the word and, but we'll make it very clear as the lecture goes on. And, or, all right, you know what or means, okay? Or you think you know what or means because there's actually two meanings to or. So there's the inclusive or and the exclusive or, and I'll show you what that means later. And then not, which is just the negation, okay? So that's what binary logic is, and that's what we'll do first. And then I'm going to use binary logic. I'm going to show you that we can build binary machines or binary circuits that can do binary logic. Okay, so binary circuits are basically little machines which are capable of performing binary logic. Okay, now why am I teaching this? I already said a little bit about that, but let me go over it formally right now. The first reason that I'm teaching it is that it's going to have practical uses later on. So, for example, when we get to spreadsheets and databases towards the end of the course, I'm going to have to make reference to logic, to binary logic. So these operators and, or, exclusive or, and not. Okay, not so much the exclusive or, but we are going to have to make use of those operators, and so yeah, it has practical purposes. Okay, and I think you'll see why when we get there. Okay, the second one is that it connects binary numbers to human language. Okay, now up till now, you saw those binary numbers and you could see how they were related to arithmetic. In fact, I reduced the usual decimal arithmetic that you're used to, that you learned in grammar school. I reduced that to binary arithmetic. But now I'm saying, look, there's something more. There's binary logic. And binary logic, even though it has a relationship with mathematics, also has a relationship with human language. Okay, and that'll especially come out when we talk about databases later on. And you can already see here that the operators, that is the things that join the binary numbers together, they're actually English words. There's like or, there's and, or. Now that XOR looks funny, okay, but it just means exclusive or. Okay, you'll see what that means in a minute. And not. So those are English words. And you know that, we call these things computers because back in the day, that's what they were used for. They were used to compute things. But you don't think of your phone anymore as a computer. I mean, you do use it as a calculator, but that's not usually what you use it for. You usually use it for communication, okay, or similar. And so like there's a relationship between computers and human language, all right? And it turns out that the same kind of thing that allows us to do human language also allows us to do in our brains. The same thing that allows for language allows for mathematics. Not totally, but like there's definitely an overlap in the human brain between those two operations. And since we're building this mechanical mind, you wouldn't be surprised that there's an overlap between this kind of logic, which is language, and arithmetic, which is a branch of mathematics. Okay, and so yeah, there's this idea of a mechanical mind doesn't just cover adding, which is what I'm going to do today. It actually covers language, and that makes these machines a little bit scary because you already know that you can almost talk to computers and they'll do what you ask them to do. I mean, your phone has text to speech and speech to text and so on, and you could give your phone commands by just speaking to it, and that's going to improve over time to the point that we'll be able to speak to computers and they'll be able to speak to us actually, verbally, and they already have that. Okay, so this is not science fiction; it's science fact, but it isn't. It just isn't that common right now. So that's another reason to study binary numbers. The next thing is that binary logic is more fundamental than arithmetic. And so what I'm going to be able to do is take arithmetic, binary arithmetic, and actually reduce it to a binary logic. All right. And so we'll see that underlying the usual arithmetic that you do, there are these very simple operations, which are logical operations, okay, which are actually linguistic in origin. All right. And then finally, the reason I'm doing this is that I can build machines that do binary logic. Now, if I can build a machine that can do binary logic, and binary logic can be used to do arithmetic, then I can build machines to do arithmetic, okay? And those are your mechanical minds, all right? So that's exactly how these mechanical minds are built. They're basically built by reducing whatever you want to do, whether it's language or math or whatever, down to binary logic. And then there are machines which do the binary logic. So there are machines that do the binary logic, and then the binary logic gives rise to the arithmetic, or it's the foundation of the arithmetic in the language. Okay, and so that's it. That's the essence of these digital machines. Now you don't know the details of how that works yet, but you will by the end of this lecture. Okay, so it should be a rewarding lecture, even though it's a little bit difficult. It should be a very rewarding lecture. Okay, so let's begin. The first thing I need to teach you about is just plain old ordinary logic. Okay, the word logic actually comes from the Greek word logos, which means word, and it's related to our word language. Okay, so logic and language, they're synonymous, but logic is very precise. Okay, and you may actually have other courses in logic. In fact, there are philosophy courses in logic where they teach you, how to look at arguments that are made and to see if those arguments make sense or if there's some kind of a fallacy in them. Okay, and it's a fun thing to do because you could apply them to commercials, and you see that commercials, like television commercials, can be very persuasive, and yet at the same time, they're just filled with like illogical statements. Okay, and so logic is kind of fun for that reason. Okay, now let's start. So let me show you how what logic is all about. Suppose that you have these two sentences. Okay, and so sentence number one here is, I am a Canadian citizen. Okay, I'm a Canadian citizen. Now, that sentence, speaking about myself, may be true or may be false. You don't know. Okay, I could be lying. All right, so, or I could be telling the truth. So I'm a Canadian citizen is a sentence which could be either true or false. And then there's a second sentence here, I am an American citizen. That could be either true or false, okay, depending on the situation, depending on who's saying it, okay. Now, in my situation, I actually am a dual citizen. So if I said I am a Canadian citizen, I'd be speaking the truth. And if I said I am an American citizen, I'd be speaking the truth. Okay. But, suppose that I were only an American citizen and I said to someone, I'm a Canadian citizen, I'd be lying. Okay. I'd be making a false statement. All right. Or suppose I were only a Canadian citizen. If I said I'm a Canadian citizen, I'd be speaking truth. But if I said I'm an American citizen, I'd be lying. Okay. Or maybe you're a citizen of neither country, in which case both sentences would be false. So, you go to the border and you say, "Are you a Canadian?" And you say yes. "Are you an American?" And you say yes. Well, you'd be lying. If you were neither, you'd be lying on both accounts. Okay. So logic is the business of taking statements, which are either true or false, and then putting them together in a compound sentence, and then determining whether that compound sentence is true or false. Okay, so let me start to get more specific here. Okay, so the conjunctions by which we can join these things are going to be and, or, an exclusive or. Not is a little bit different. It doesn't join two sentences together, but those are the conjunctions, if you like, that we're going to study. So let's start off with and. And you say, well, how does and work? Okay, so and joins two sentences. Okay, and it gives a resulting sentence, and that resulting sentence is either true or false. So the original sentences are either true or false, and then the joined sentence is either true or false. And the way and works is only if both of the individual sentences are true, when they're joined together, do you get true, okay, as a result. Otherwise, the sentence that you get is false. If either of the two individual statements are false, or if they're both false, then when you join them together with and, it turns out that the resulting sentence is false. Okay, so that's a little bit abstract, so I need to make that clear for you. Okay, so let's take a look at the sentence that you would get if you join together the two sentences that we looked at above. Okay, so I could say I am a Canadian citizen, and I am an American citizen. Okay, so those are the two sentences above. I am a Canadian citizen, and I join it together with the second sentence, I am an American citizen, with the word and. Okay, now as I said, I am both. So this first sentence here is true. I stated a true statement. And the second sentence here is true. So I stated a true statement. And so the two sentences are joined together like this. A true sentence is joined with and to another true sentence. Okay, the way and works is if both sentences are true, the resulting sentence is true. That's the only time you get true. So if you have true and true, in other words, a true sentence joined together with another true sentence with and, so true and true, that yields the answer true. Okay, there's our first logical operation. It can be applied to any sentence that you like, as long as that sentence resolves to either being true or false. You can join it with another sentence that resolves to true or false to get a compound sentence, and then that compound sentence is either true or false. And if the conjunction is and, then only if both of the sentences are true is the resulting sentence true. Okay? So once again, I am a Canadian citizen. True. Okay? And I am an American citizen. Also true. So I am a Canadian citizen and I am an American citizen. True, because both are true. Okay, so there's one of the four possibilities. Let's go on. Okay, now suppose I have the same sentence again. Whoops, what am I doing here? Okay, suppose I have the same sentence again. Okay, but this time suppose that I'm only an American citizen. All right, so in other words, if I were to say I'm a Canadian citizen, I'd be lying. Okay, but if I say I'm an American citizen, I'm speaking truth. I'm a Canadian citizen, I'd be speaking false. I'm an American citizen, I'd be speaking true. Now in this case, this compound sentence here reduces to the joining of a false sentence with a true sentence. And if you have false and true, okay, the result is false. Remember, both have to be true to get true, otherwise you get false with and. Okay, and so you can conclude that false and true is equal to false. All right, now think about it. Okay, so sometimes people get lost at this point because it's getting a little bit abstract, but just think about it. Just pretend that I'm only an American citizen, and I get to the border and I say I'm an American citizen and I'm a Canadian citizen, or I guess the other way around, the way I have it written right here. Okay, I would say I'm a Canadian citizen and I'm an American citizen. I just lied. It's true that I'm an American citizen, but if I'm not a Canadian citizen, I'd be lying. Okay, and then the resulting sentence is false as well, because the and says both of these are true. And so if one of them is false, you're asserting a falsehood. Okay. It's a little bit awkward because we usually don't say I'm a Canadian citizen and I'm an American citizen. You would say something like I'm Canadian and American. Okay. But just think about it that way. Imagine that you're only American, you're only an American citizen, and you get to the border and you say I'm Canadian and American. You lied because you're not Canadian. Okay. And so that's what and does. It insists that both sentences be true in order to be true. Okay, so there you go. Now, I'm not going to go through all the possibilities because I think you can see how this works, but we could summarize them here. And I'm not going to give examples of all the possibilities, but you can see how this works here. If both of the sentences are true, you get true. Okay, and that's the only case in which you're going to get true. If both sentences are true, the resulting sentence is true. If either of the sentences are false, or if both sentences are false, the resulting statement is false. Okay, so there you go. That's how and works. All right. Now, at this point, this is just like language. It's like, basically I just told you how and works. And you say, I knew this already. I know. But now we're going to make the connection to binary numbers. So I can now associate the number 1 with true and the number 0 with false. Okay. And this is the genius of George Boole, because he's the person who came up with Boolean algebra, and he made the association with true and false, 1 and 0, and that's where you get all the connection between binary logic and binary arithmetic that we're going to do later. Okay, or we're going to do as I continue in this lecture. Okay, and so this table here, which can be called a truth table, okay, basically reduces to this here. Okay, now notice it looks a lot like arithmetic, doesn't it? Okay, so over here the first one is 1 and 1 is equal to 1. Okay, it kind of looks like 1 plus 1, okay, is equal to 1, except that first of all that's wrong. Okay, 1 plus 1 is not equal to 1. 1 plus 1 is equal to 1, 0. All right, but it kind of looks like that, and so this addition here, that is known as the operator. Okay, that's the thing that joins the pieces together. It operates on the rest of the numbers. Okay, and so here, instead of having an arithmetic operator, we have a logical operator. And so logical operators, just like arithmetic operators, take two binary numbers and they join them together. Okay, and so here we have 1 and 1 is equal to 1. Don't think of that and as plus. Okay, sometimes in English we'll say 1 and 1 is 2. Okay, no, that's not what this and is. This and is the logical and so true and true is equal to true is the way you should think of that. Or writing it in binary, 1 and 1 is equal to 1. Okay, but if either of either the first number or the second number or both are 0, you get 0. Okay, so 1 and 1 is 1, but 0 and 1 is 0, 1 and 0 is 0, and 0 and 0 is 0. Okay, so there you go. You've learned your first logical table. Okay, now this doesn't look like a table. Those are the four possibilities, but you can write it as a table, and there it is. Okay, now what's a table? It's just like like your multiplication table. Okay, you say, well, what's my first number? Well, say I'm doing this one right here. Okay, so 0 and 1. Your first number is 0, so you go, okay, 0. So I'm in row 0. And your second number is 1, so you go, okay, here's 1. And the conjunction between that row and this column here is this number there, and that gives you the answer. Okay, 0 and 1 is equal to 0, like that. Just like a multiplication table. In fact, it is a multiplication table. And so you might not have realized this, but binary logical AND is the same as binary multiplication. There's our first connection between logical operators and arithmetic, binary arithmetic. Okay, so remember how multiplication works. If you go 0 times 0, that's equal to 0. Or you go 0 times 1, that's equal to 0. Or 1 times 0 is equal to 0, and 1 times 1 is equal to 1. Only if you've got both 1s do you get 1 when you multiply them together. But we didn't get to it by multiplication or thinking in terms of math. We got to that table thinking in terms of logic. And the logic was exactly what I gave you above. Only if the two sentences are true when you combine them with and, do you get true, otherwise you get false. Okay, and so this is a discovery. It's a mathematical discovery that George Boole made, and other people of his time, okay, mid 1800s. And basically they discovered that the same kind of the same cognitive operation that does and is the same as the cognitive operation that does multiplication, at least in binary. Okay, so you can see there's a relationship between logic, language. Whenever I say logic, you should think in the back of your mind language. There's a relationship between language and logic. Okay, and here's the beauty: we're going to make a machine that does this. All right. Okay, so there we go. There's and. Okay, now what's the next one? The next conjunction we're going to look at is or, and the way or works is if one or the other sentence. So if at least one of the two sentences is true, the resulting sentence, the conjoined sentence, is true. Otherwise, it's false. Okay? So let me say that again. If at least one of the two sentences is true, the resulting sentence that is joined with or is true. Okay? Another way you could think about it is the only way you can get false if both of the sentences are false. Okay? So if one is true, or the other is true, or both are true, it's true. Otherwise, if they're both false, then it's false. Okay, and so now let's go through our example. Here's my example. I am a Canadian citizen, or I am an American citizen. Okay, so if I'm both, and someone said to me, you are a Canadian citizen or you are an American citizen, I'd say yes, because I'm both actually. Okay, or if I were to just say I am a Canadian citizen or I'm an American citizen, that would be true. Okay, because at least one of the two is true. Okay, a little bit awkward, but it's true. Okay, so if you're Canadian citizen and an American citizen, it's true. Okay, but it's also true if one of the two are false. Okay, so if you're a Canadian citizen but you're not an American citizen, it's still true. Okay, and you might think of it might work a little bit better if you think of it in terms of a question. Now, if someone said to you, are you Canadian or American, and you're one of them, you would say true. Okay, because the word or says I'm not that picky, either one or the other. Okay, or both, one or the other, or both. Okay, so if you're a Canadian citizen and not an American citizen, the sentence is still true. And the other way around, if you're not a Canadian citizen but you are an American citizen, it's also true. The only way you're going to get false out of this sentence is if you're neither Canadian nor an American citizen. So imagine, I don't know, imagine you're an Italian citizen. You're not Canadian, you're not an American, you're just an Italian citizen. And someone asks you, are you Canadian or American? You'd have to say no. Okay? All right, or conversely, asserting, if you're only an Italian citizen, asserting, I'm a Canadian or I am an American citizen, you'd be saying something false, okay, because you're neither one of those. All right, and so that's how or works. Okay, so let's make that a little bit more formal now. If you turn that into like a table like we did before, purely in terms of true and false, if both sentences are true, then the answer is true. So true or true is true. Okay, if one of the two sentences is true, and it doesn't matter which one, okay, the order doesn't matter. Okay, that in mathematics is called commuting. So it means that logic is commutative. You know this, like 3 plus 4 and 4 plus 3 are the same. Okay, so it doesn't matter which order you add things in. And so it's the same in logic. It doesn't matter which order you do the or in. So if one is false and the other is true in either order, you're still going to get true. Okay, so false or true is true, or true or false is also true. The only way you're going to get false is if both sentences are false. So false or false yields false. Okay, there you go. So this is in terms of the words true and false. But if we replace that in terms of the binary, where 1 represents true and 0 represents false, then you can write this, and basically this says 1 or 1 is 1, 0 or 1 is 1, 1 or 0 is 1, 0 or 0 is 0. Okay, so another operator. Or if you want to write this as a table, there it is. Okay, so again, like if you wanted to do this one, your first number is 1, and so you go, okay, there's my first number, and like in this column here, my first number, is it 0? Is it 1? Well, my first number is 1, so okay, pick 1 there. And my second number is 0, okay, there, like that. And then you just cross-reference them, this row and this column here, and you get that. So 1 or 0 is 1, and there you go. Okay, and so that's your OR table. You might look at that and go, is that addition? And the answer is no. It's neither addition nor multiplication nor subtraction. It's basically like no arithmetic operation. So and is like binary multiplication, or is like neither addition nor multiplication or division or anything like that. Okay, so this is new. This is a whole new table that you've never seen before. Okay, now this OR is known as the inclusive OR. All right, and the reason it's called an inclusive OR is because it's possible for both sentences to be true. All right, so one sentence can be true, the other, and independently, the other sentence can be true as well. Okay, that's not always the case. Sometimes you're in a situation where if one sentence is true, the other one has to be false, or vice versa. Okay, and an example of that, American and U.S. citizen, Canadian and American citizenship, they are mutually exclusive, which means you can be Canadian or not Canadian, and American or not American, independently of one another. Okay. Incidentally, that's not true of all citizenships in the world, but because Canada and the U.S. are on such friendly terms, it is possible to retain your Canadian citizenship when you become an American citizen, and so you can be both. Okay, but that's not always true. Okay, so an example, probably a better example than citizenship, is this one here. Suppose we're going to take a trip tomorrow. Okay, and I say, look, we can either go to Niagara Falls, or we can go to New York City for a trip, okay, for a day trip. But you can't do both. You can't be in Niagara Falls and in New York City at the same time, okay? So if you say, okay, we're going to go to Niagara Falls, well, then you're automatically saying, you're excluding and automatically saying that you're not going to New York City, and vice versa, okay? And so sometimes you have to choose between two things where one has to exclude the other, and this is known as the exclusive OR, okay? Now, in English, we have one word that we use for both the inclusive OR and the exclusive OR, and that's the word OR. Okay, do you want to go to New York City or do you want to go to Niagara Falls? We just say that. We don't say a special word. We don't say Zor. I mean, it'd be funny. I go, do you want to go to Niagara Falls? Zor, do you want to go to New York City? Okay, well, some languages do. Okay, there are some languages where they distinguish between the inclusive and exclusive OR. We can tell in English because of the context of it, okay? Your mind simply knows that you can't be in two places at once, and so your mind automatically knows that you're dealing with an exclusive OR, okay? If someone said you want to go to Niagara Falls and New York City, and you answer back, yeah, we're going to both, and you go, well, you can't be in two places at once, so the context resolves the fact that you're actually, that OR in that case is actually an exclusive OR, okay? But we're going to build a machine that does this, and so we have to be very precise. And so the way exclusive OR works, without going through examples of sentences, the way exclusive OR works is it looks almost like the OR. Everything looks the same except for this one, okay? You cannot have both sentences being true. If you try to make both sentences true, you're making a false statement because you can't be in two places at once in my example, okay? And so the exclusive OR is just a little different. It's false exclusive OR true is true, true exclusive OR false is true, false exclusive OR false is false. With OR, true or true gives true, but true exclusive OR true gives false, okay? And that's the only difference between the two tables, okay? So writing that in terms of binary, it looks like this. And I made a mistake, didn't I? Ha ha ha, right there. There you go. I'm kind of glad I made that mistake because this is true, okay? So let me just show you what the difference is. So if you've got 1 or 1 is equal to 1, okay, that's correct. But if you put an exclusive OR there, like that, well then 1 exclusive OR 1 is 0. The rest is the same. Here, whether you're doing OR or exclusive OR, you get the exact same answer. It's only this one. When they're both true, for OR you get true, for exclusive OR you get false, okay? And so that's the subtle difference between the two, all right? And here it is as a table, okay? And you can see this table looks exactly like OR, except right here, okay? For the OR, that would have been a 1. For exclusive OR, it's a 0. Why? Because 1 exclusive OR 1 is 0. All right, there you go. So we've looked at 3 logical conjunctions so far: and, or, and exclusive OR. And there was a 4th logical operator, but it's not a binary operator. It doesn't take 2 numbers and joins them together. It just takes 1 number and inverts it, okay? And that's not. All right, so how does not work? Well, suppose I made the statement, I'm a Canadian citizen. Okay, well, that's either true or false. Suppose it's false. Suppose I'm not a Canadian citizen. Okay, so if I said I'm a Canadian citizen, I'd be uttering a falsehood. Okay, I'd be saying something false. But then if I put the word not in there, suddenly I'm saying something true. So if it's false that I am a Canadian citizen, then it is true that I am not a Canadian citizen. And conversely as well. So if I made the statement I am a Canadian citizen and it's true, well then if I said I'm not a Canadian citizen, I'd be uttering a falsehood. Okay, and so that just reduces to this in terms of logic. Something that is not true is false, and something that is not false is true. Okay, they not just inverts the 2 possibilities. In binary, that turns out to be this. Okay, so not 0 is 1. And not 1 is 0. All right, because there's only 2 possibilities. If you're saying it's not 1, well, then it's got to be 0. And if you're saying it's not 0, then it's got to be 1. Okay, and I don't know, just for completeness, I put a table here, but I'm not exactly sure how you'd even make a table. Basically, this is just trying to make a table where not 0 is 1 and not 1 is 0, like that. Tables are good for binary operators, but this is a unary operator. It just works on 1 number and converts it to the other one. Okay, so great. There you go. There's logic. Okay, now in a little tutorial video after this, we'll do some binary logic problems. They're really simple because all you have to do is memorize those tables. And at first, like anything, this seems kind of strange. That how logic works and all that. But you'll get used to it very quickly, and past experience is anything, people do very well in this part of the course because it's once you've got it memorized, it's done. Okay, so all right, now next thing, we're going to use logical operators by themselves later in the course, so they've got applications. But right now I want to show you that I can take binary arithmetic and I can reduce it to binary logic. You already saw that with multiplication, but I'm more interested in addition, okay? And so, because we're going to build an adding machine, all right? So I want to do 2-bit addition, and I want to reduce 2-bit addition to binary logic. Now, what do I mean by 2-bit addition? So remember, a bit is a single binary digit, okay? So here's an example of 2-bit addition right there. So if I go 0 plus 0 is equal to 0, okay? Now, you say, well, why do I have 2 zeros there? Well, really, I have this, okay? I just have that 0 plus 0 is equal to 0, okay? All right. Now, I put the carry in there on purpose because when we build our little adding machine, we're going to need to take care of the carry as well as the least significant figure, okay? So 0 plus 0 is equal to 0. The way you can read that is 0, which is a bit, plus 0, which is a second bit, so this is 2-bit addition, is equal to 0, carry 0. Okay, that's what that means there. Okay, and there's 4 possibilities. 1 plus 0 is equal to 1, carry 0. 0 plus 1 is equal to 1, carry 0. And then finally, 1 plus 1 is equal to 0, carry 1. There you go. There are the 4 possibilities. All right, you've seen this before. I did always put the carry in. I've purposely put all the carry in here because it's going to be an object of interest as I go on. Okay, now there are 4 possibilities, but take a look at the form of the answer. Okay, every one of those answers has 1 bit plus another bit is equal to 2 bits. Okay, and what is that? How could we name that? Okay, what is that form? The first bit we can call A. The second bit we can call B. This bit there is the carry, which we will call C. And that 0 there is usually called the least significant figure, which is a long name, which I don't know what else you'd call it. It means basically the number or the bit on the right. Okay, so the carry is the one we write on the left, and we carry into the next column if we're doing multiple column addition. But the carry is what you carry, and then there's the least significant figure is the thing that you would write underneath the line. Okay, so that number, that number, that number, that number, that's the least significant figure. This number, that number, and that number, those are the carries. Okay, and you can see that all of them have this form here like that. All right, and once again, those A and B are the two numbers you're adding. C is the carry, and L is the least significant figure. Okay, now that's that form I want to rewrite now in terms of logical operators. So you go, well, which logical operators do you need? We'll see. First thing is take these four possibilities here, and just ignore the carry for now. Just write down the least significant bit, least significant figure. Okay, so that's what I did over here. So if you take what I had above and you say, you know what, I'm just going to get rid of the carry and I'm just going to write down the least significant figure, you get this addition here. Now it's incomplete. Okay, that's why I put LSF at the end here. LSF meaning I'm filtering out just the least significant figure and I'm throwing away the carry. If you do this, you get 0 plus 0 is equal to 0. Okay, and the carry is thrown away. And then you have 1 plus 0 is equal to 1 and the carry is thrown away. 0 plus 1 is equal to 1 and the carry is thrown away. 1 plus 1 is equal to 0 carry 1, but I'm throwing away the carry, so 1 plus 1 gives me just 0 for the least significant figure. Okay, so I hope you see what I did there. Basically, I just copy and pasted this, okay, but then I just remove the carry like that. I just remove those numbers there, and I get that. Okay, and now I say to you, we just studied the those logical operators. Does this look like any one of those logical operators? Okay, and so in other words, I'm asking 0. I can actually write it like this. Let me just do it. I'll just do it for this one. Let me just rewrite this here like that. Okay, and I could say here, I could just put a question mark like that. All right, so we're looking at this table here like that. Okay, and I say to you, what logical operator would you want to put in that question mark that would make this table work? Okay, so I want this whole table to work right there, and I say to you, what logical operator would I put in there? Well, you could go through them. There's, we've only got 3 possible binary operators, so let's try AND. We'll start with AND. And you go 0 and 0. So pretend that the question mark is 0. 0 and 0 is equal to 0. Okay, well that one worked. But then you go 1 and 0. 1 and 0 should equal 0, but you're getting 1 here. Okay, so that question mark cannot be AND. Because if it were AND, you would get 1 and 0 is 0, but here you're getting 1 as an answer, and so it can't be AND. Okay, so throw away the AND. Let's try OR. That's the next one. So you go 0 or 0 is equal to 0. Well, that worked. If you go above and you take a look at the table there, 0 or 0 is equal to 0. That works. Okay, and then you go 1 or 0 is equal to 1. That works. Okay, 1 or 0 is equal to 1. And so it works the other way around because it commutes. 0 or 1 is equal to 1. But what's 1 or 1 equal to? 1 or 1 is equal to 1. And look here, 1 or 1 is equal to 0. So it can't be that one. It has to be the exclusive OR. Okay, and let's see if it is. Okay, 0 exclusive OR 0 is 0. That works. 1 exclusive OR 0 is 1. That works. 0 exclusive OR 1 is 1. That works. 1 exclusive OR 1 is 0. That works. So you conclude that the question mark must be the exclusive OR. Okay? Now, what did I just show you? What did I just prove here? What I proved is that when you do the addition here like that, you add 2 binary bits, you actually get 2 binary bits out. So 2 binary bits go in and 2 binary bits go out. The binary bit that comes out, that's the least significant figure, that is obtained from A and B using exclusive OR. Okay, so let me say that again. The least significant figure is obtained from the 2 numbers using exclusive OR. All right, so here you go. You can now say that in order to get L, okay, which is the least significant figure from A and B, which are the 2 numbers that we're adding together, in order to get that, you have to use exclusive OR. So A exclusive OR B gives you the least significant figure. All right, Great. Let's do the same thing now for the carry. So you go back to our original addition here, and you go, okay, throw away the least significant figure and just concentrate on the carry right there. What you get is this table here. Okay, remember the least significant figure has been thrown away. So what do you get? Well, if you go 0 plus 0 is equal to 0, carry 0, and I'm just writing that down. 1 plus 0 is equal to 1, throw that one away, carry the 0, so just keep the carry. 0 plus 1 is equal to 0, carry, 0 plus 1 is equal to 1, carry 0, so you get a carry of 0. 1 plus 1 is equal to 0, carry 1. Okay. In other words, the only time you get a carry is when you add 1 plus 1. Okay. And you can see that above here. Go back to the original addition. There's no carry unless you're doing 1 plus 1. Okay. And so now you could do the same thing here. I mean, I've got that plus in there, but you could say, you know what, let me just take this whole thing and let me put a question mark in here. Okay. Because I want to ask what logical operator gives me the carry, and you can go through them and you can see that 0 and 0 gives you 0, that works. 1 and 0 gives you 0, that works. 0 and 1 gives you 0, that works. 1 and 1 gives you 1, that works. And so you can conclude that the unknown operator that gives you the carry is AND, just like that. Okay, so above the question mark must be exclusive OR. Here the question mark must be AND. All right. So now we can write that A combines with B using AND to give you the carry. In other words, A and B gives you the carry. Okay, so back to our 2-bit addition, which had this form. Basically, that form, A plus B, gives you a least significant figure plus a carry. So A plus B gives you CL. All right, I can reduce that addition. All right, so this is an addition to two logical operations. Okay, so addition turns out to be a combination of exclusive OR and AND, both together. All right, so what have I done? Well, I mean, I could do this with all of arithmetic, by the way, not just with addition. But I only need to show it to you so that your mind can sort of understand how computers are built. That's the whole point of this lecture, is how do computers do what they do, okay? And basically I said, look, we got this thing that we do with our brains called arithmetic. And I just showed you that I can take arithmetic and I can reduce it to logic. Okay, and there it is. So adding here turns into two logical operators. And you go, okay, well, that's kind of interesting. And here's the point. I can build a machine that does exclusive OR, and I can build a machine that does AND. So if I can build a machine that does exclusive OR, and I can build a machine that does AND, what does that mean? It means I can build a machine that can add. All right? And so that's your mechanical mind. Okay? Let me broaden it out. I can build a machine that does all of those logical operators. Any arithmetic can be reduced to logical operators. I can build machines to do those logical operators. Therefore, I can build machines to do arithmetic. Okay? Now I have a calculator. Expand it out even more and say, well, what about complicated operations like we do in language? Language can be reduced to logic. Logic can be built in terms of these machines. Therefore, you can build a machine that does language. Okay? And there's your mechanical mind. All right? Now, before I show you how that works, because I'm going to do that, the first thing I got to do is show you the symbols for the circuits for AND, OR, and exclusive OR. Okay, so I'm going to start designing circuits for you. What does that mean? I'm going to start designing things that you would literally wire up in the lab. Okay, and you would go into a lab, and you could actually buy kits, at Radio Shack and things like that. So if I don't think, well, we don't have an education major anymore, but if any of you were education majors, you might want to teach this in a classroom setting, on say arithmetic or something like that. You might want to show them logic. You can actually go buy these kits, and you can wire up the kits, okay, wire up the components, and you can actually build a little calculator for students and show them what I'm showing you in this lecture. All right. Now, to do that, because I'm not going to physically build this thing for you, I need symbols, okay? Kind of like a map, like if you're building a house or architecture plan. If you're building a house, you got to draw walls and things like that. So that's kind of what I'm going to show you, okay? And so these symbols that I'm going to show you are the circuit symbols for the logical operators that we're going to need, okay? So a NOT gate is basically just this triangle. Notice that on the left side, there's this one wire coming in, okay? And on the right side, there's just one wire going out. And that's the way NOT works. 1 bit gets converted into 1 bit. So the way to think about this is that if you've got like a 1 coming in here, the NOT gate turns it into a 0. Conversely, if you've got a 0 coming in here, you got a 1 going out, okay? Now, I'll do that a little bit better in just a minute, but let's look at the other symbols, and then we'll come back to the NOT and some of the other ones as well, and try to explain just how they're working. So this one here that looks like a bullet, it's kind of flat in the back here, and it's kind of rounded in the front. That's the symbol for an AND gate, okay? And now AND, what it does, remember, is that it combines 2 bits, and it gives you 1 answer. And so on the left side, you can see that there are 2 inputs. These 2 wires here are like 2 inputs. And out here, that's your output, okay? So that's your AND gate, rounded in the front. Your OR gate looks like an arrowhead. You can see how it comes to a point there like that, and it's kind of got this curve in there like that. And again, the OR takes 2 numbers in, 2 bits in, and it gives you 1 bit out. And the exclusive OR looks like the OR, but it's got that extra little fin in the back here like that. Okay, so there you go. This is the NOT, the AND, the OR, and the exclusive OR as a diagram, because I'm going to be diagramming out the machine, the circuitry that actually does the computing. So to try to explain just what's going on here, I'm going to draw on this. Let me I guess use red here, okay? Suppose that I feed this thing a 1, okay? So that little 1 there, let me see if I can make that a little bit bigger for you, maybe. View, zoom in. Yeah, that's a little bit better. Okay, so that red 1 there, that's like a 1 going into the NOT gate. Okay, so the NOT gate here does something. There's some circuitry inside of it here. Okay, and I'm not worried. We'll worry about that circuitry in a minute. Okay, and then what comes out is a 0. Okay, so basically the NOT gate will change that 1 into a 0 like that. Okay. All right, so conversely, if I feed it a 0, let me write it above. That's a little bit better. Okay, if I feed it a 0 here, a 1 will come out like that. Okay, because that's what NOT does. It changes 0s into 1s and 1s into 0s. Now, at this point, you're saying, well, how is that a machine? Like, how do you feed a 0 to a machine? Well, it depends actually what you're making the NOT gate out of, but our NOT gates are made out of like electronic components, out of transistors. You can make them out of lots of different things, which we'll talk about in a minute. But that 0 is like low voltage. Okay, so you're actually feeding a voltage in here. And now I don't want to get into too much of the detail, but basically the way the NOT gate works is that if you feed low voltage here, so this is low, you get high voltage out here. Okay, and your higher voltage, like your low voltage might be like 0 volts, and your high voltage might be like 5 volts. So if you feed a NOT gate a 0 volt, out comes 5 volts. And if you feed it the other way around, if you feed it 5 volts here, then what comes out is 0 volts. Okay, so basically, you could think of the 5 volts as kind of being like the 1, and the 0 volts as being like the 0. Okay, so these things, when I say you feed it a 1 and a 0, what I'm really saying is you apply voltage to them. All right, but we don't have to get into all the details. But these are physical things, so you are really building them with like batteries and switches and so on. All right, okay, and what about the AND gate? How does that work? Well, remember how AND works. If I feed it a 0, say I feed one of them a 0, so that's going in there. Okay, and I feed a 1 on the bottom here like that. Well, what does AND do? Only if they're both 1s. Okay, only if both of these are 1s will you get a 1 out. Okay, well, one of them is a 0, so you get a 0 like that. Okay, in other words, it's a machine which does exactly what and logical AND does. Okay, so you feed it a 0 and a 1, and a 0 comes out. Well, what if I fed it a 1 and a 1? Feed it a 1 and a 1. Well, and 1 and 1 is 1. Okay, and again, those 1s would represent some high voltage, like say 5 volts, and the 0s would represent low voltage, like 0. Okay, and it doesn't matter, like you can feed it 2 0s, And you say, well, what's 0 and 0? Well, 0 and 0 is 0, like that. Okay, and I'll actually demonstrate this in a minute, but I just want to, at this point, make sure you understand how these diagrams are to be interpreted. What about OR? Well, if I feed an OR a 0 and a 0, so 0 or 0 is 0, you get a 0 like that. Conversely, I could feed it a 1 or a 0, and remember, 1 or 0 is 1, so we get a 1 like that. Okay, and I won't go through all the possibilities. And what about the exclusive OR? Well, exclusive OR, if I feed it two 1s, out comes a 0 like that. Okay, so each one of these are basically machines that operate just like the they're machines that basically operate like the logic that they're supposed to be emulating. Okay, so let's go back here for a second. And can I build a machine which does this? Okay, well, I don't have a machine that does the addition directly, but I have a machine that does and I have a machine that does exclusive OR. So with those two machines together, I should be able to make a machine which does addition. Okay, and so there's this wonderful site. Let me bring that site up for you. This will take just a second. Oh, no. There it is. Okay. All right. So there's this site, and it's a little hard to see up here, but the URL up here is logic.ly. Okay. And I actually have it linked from our Canvas site. Okay, and it's basically an online little web page where you can build circuits. Okay, and so it's logic.ly demo is the demo. Okay, so let's build some circuits. So first of all, let me show you how you can build a circuit. So this is just a switch. Okay, so over here it says toggle switch, and what I did was I basically pulled in a switch, and over here this is a light bulb like that. Okay, now I can attach my switch to the light bulb like that. And how does it work? Well, right now you notice how that switch is white. That switch is in the off position and the light bulb is off. And now if I click the switch is on and in the on position and the light bulb is on. Okay, so basically, there we go. This is kind of an on-off switch. This is exactly how your switches work in your house. Okay, off, on, off, on. Okay, notice when the switch is on, it's kind of got this blue around the outside, and the light bulb is blue, that's on. And when the switch is off, it's got a white border here and the light bulb is off. Okay, let's get rid of the light bulb and let's start adding some of those gates. Okay, so over here there's a whole bunch of gates. I didn't teach you all the gates. Okay, there's a whole bunch. Let's just play with the NOT gate right now. So over here you can see that I'm just grabbing and dragging the NOT gate in there, and then let me drag in a light bulb as well. Okay, and so right now I've got 4 pieces and 3 pieces, and let me join them up. Let me attach the switch to the input of the NOT gate here. So there's the NOT gate, and I've attached the switch to the NOT gate, and then I'm going to attach the NOT gate to the light bulb, and ta-da! When the switch is off, the light bulb is on. When the switch is on, the light bulb is off. Okay, so that's what a NOT gate does. It does the exact opposite. In fact, I can put the two side by side. Let me do that. Let me grab a NOT switch here. A switch and a light bulb like that. Notice that when the top switch is on, when the top switch is off, the light bulb is on. When the bottom switch is off, the light bulb is off. When the top switch is on, the light bulb is off. When the bottom switch is on, the light bulb is on. Okay, so they do the exact opposite. So what's doing that? The NOT gate. That's exactly what the NOT gate does. Okay, so a fun little site that you can play with. And let me get rid of all the pieces here. Actually, I need the 2 switches. So let me grab those 2 switches like that and put this switch a little closer like that. Okay, and now how do we make a 2-bit adder? Well, it's made up of 2 pieces. It's made up of an AND gate, and it's made up of an exclusive OR. Okay, and how does this work? Okay, and then there are 2 outputs as well. So I'm going to need 2 light bulbs. Okay, like that. So those are all the pieces. There are 2 inputs, and these 2 inputs here are the 2 switches. What are they? Those 2 inputs are like A and This other one is B. They're like the numbers, you know, in the text there. Oops, not A, but B here, like that. Okay. So the top switch is like A and the bottom switch is like B. Okay. Now, if I feed the two switches, A and B, to the exclusive OR, okay, so if I feed one switch and then the other switch to the exclusive OR, so I'm feeding A and B to the exclusive OR, what am I getting? What do you get out of exclusive OR? You get the least significant figure. There it is. Okay, so remember, two switches together fed through the exclusive OR gives you the least significant figure. Okay, if you don't remember that, let's just go back very quickly here. What have I done so far? So far, I have done just this piece right there. Okay, you take add, you combine it, you take A, you combine it with B using exclusive OR, and you get out L. Okay, how do you get the carry? Well, the way the carry works is you take A and you combine it with B using and you get the carry. So if we go back here, all right, so now I have to feed the same two, but now to the and. So if I feed A to the and if I feed B to the and, now this might look a little funny there that's crossed there. These two that are crossing, they don't touch, okay? So basically this just says, look, I'm feeding A to the and gate. I'm also feeding B to the and gate. What do you get out? Out of that, you get the carry. So over here, this is the carry. Like that. All right. And there you go. You've got a 2-bit adder. Let's see if it works. Okay. So right now, if I've got both switches off, so that means like A is 0 and B is 0. Well, what do you get when you add 0 plus 0? Okay. So A is 0 and B is 0. What you get is 0 down here. Okay. Carry 0 up here. Okay. And you can see that both light bulbs are off. So this basically says that 0 plus 0 is equal to 0 carry 0. All right, well, let's do, how about we do 1 plus 0? So if you go 1 plus 0, you get 0, you get 1 plus 0 is 1 carry 0, okay? So A is 1, B is 0, so 1 plus 0 is equal to 1 carry 0. All right, so you can see that it's working there. We'll go through all 4 possibilities, okay? What if I did 0 plus 1? So now instead of A being 1, now A is 0 and now B is 1. Okay, instead of being 0 the way it was a minute ago. So now I've got 0 plus 1 is equal to 1 carry 0. And then finally, if I add 1 plus 1, so 1 plus 1 means that both A and B are 1. So 1 plus 1 is equal to 0 carry 1. Okay? And you can see that I've gone through all 4 possibilities. I'll do it again very quickly, but I've gone through all 4 possibilities, and what you can see is that you get the right answer all 4 ways. And so what we've done is we've effectively designed a 2-bit adder. Okay, so let me go through them again. So right now I've got 0 plus 0 is equal to 0 carry 0. Okay, and now I've got 1 plus 0 is equal to 1 carry 0. And now I've got 0 plus 1 is equal to 1 carry 0. And 1 plus 1 is equal to 0 carry 1. Ta-da! By taking the 2-bit addition and reducing it to 2 logical operators, and by using machines to emulate those logical operations, I've basically been able to build a 2-bit adder. Okay, so you can see how I'm starting to get to a machine. The only thing at this point, and I think this is the hardest part of the lecture, the next part, you know, the only thing now is you could say to me, well, okay, you know, like you said, there's these machines, you know, like go back to this. You say, look, you know, you can make this machine here, you know, like an AND, all right? Or you can make an exclusive OR machine. And you go, but how do you do that? How do you actually build a machine that emulates AND or emulates OR? Okay, now to do that, I have to describe how transistors work. Okay, so you don't really need transistors to build computers. You can build computers out of any switches that are in the 1 or the 0 position. Okay, and that can be flipped. okay, by other switches. All right, but today we build these our computers out of transistors. You could, believe it or not, build a computer, like an AND gate using using water hoses and valves. Okay, I mean that sounds a little bit strange, but anything which either allows the water to flow or doesn't allow the water to flow could be a 0 or a 1. Okay, and you could do it out of anything which is basically is in a state of either a 0 or 1, and that you can then connect that 0 to 1 to another switch which does a 0 to 1, or another switch which does 0 to 1, and so on. Okay, so a transistor is just a very, very tiny electronic switch. All right, it's a very tiny electronic switch. Let me show you how you can build a NOT gate out of a transistor. Okay, in fact, a NOT gate is just a plain old single transistor. All right, so let me switch here to another screen, and there we go. Okay, that's a little small. Let me increase the size and zoom in. Let me zoom in a little bit more. There we go. Okay, now what you're looking at is the schematic for a transistor. A schematic is just like a little drawing that represents what a transistor looks like. I'm actually going to show you pictures of transistors in my next lecture, but let me just describe to you what you're looking at here. Okay, what you're looking at here is a device which has 3 leads, 3 outputs. Okay, or 3 wires. So let me draw on this. I'll draw the wires. I'll highlight them in blue. There's one wire here. Okay, you can see where that blue line is at the bottom. This is the ground. That's kind of like the supply of electrical pressure. Okay, now these are made out of electricity, but if you don't have a good intuition to electricity, you might want to imagine that this is like a garden hose. And garden hoses have pressure, and where does that pressure come from? Well, you attach the garden hose to your house, and there's water pressure in your house. So that lead there that's called ground, that's like the water pressure from the house. Okay, now what does that pressure do? That pressure wants to push the water up through here, and never mind the input for a minute, but it wants to push the water through here, through there, like that, and so that it squirts out there like that. Okay, so that blue line that you're seeing is the where, if this were a garden hose, where the water would want to flow. Okay, so that blue line is where the water wants to flow. Now these really are electronic devices. I'm just using water as a metaphor. So that blue line is the direction in which the electricity would like to flow. But you can think of the electricity flowing like water flowing. Okay, and so it flows this way. It flows up through there, it flows up through there, it flows up through there like that, and then it flows out like that, and then you can imagine it squirting out through the top. Okay, so there's your garden hose. And now what does that input do? Well, the input is kind of like a valve. And so if you don't apply any electricity to the input, the water flows the way it does. Okay, and so let me do this part in red. If you apply no input, no voltage to the input, okay, then you get water flowing out like that. All right, so notice that I wrote those as zeros and ones. So if at the input I don't apply any electricity, at the output I do get electricity. So nothing in, 1 out. All right, so you could already see this is kind of like a NOT, because what does a NOT do? It changes a 0 into a 1. But a NOT also changes a 1 into a 0. And so not only does it do this, but it also does this. If I have a 1 here, what happens is that now the flow gets cut right there. Okay, and if the flow gets cut, this part here, there's no flow there now. Okay, why? Because imagine that it's like a valve where you just close the valve off so that water can't flow through the valve. Or another way, if you want the image of the garden hose, you're not supposed to do these to hoses, but like if you kink them, the water can't flow around the kink, and so there's no water that flows out of the hose. And so by applying electricity to the input, you get no electricity out. Okay, and so you have both possibilities. If you apply electricity to the input, you get no electricity coming out of the output. Conversely, if you don't apply anything to the input, you get electricity coming out of the output. All right, so in summary, what you're getting is If you apply a 0 to the input, you get electricity coming out. If you don't, let me say that again, make sure I said it right. If you don't apply anything to the input, then you get electricity coming out of the output. If you do apply electricity to the input, then you don't get any electricity coming out. And ta-da, your single transistor is basically converting a 0 into a 1 and a 1 into a 0. Okay, so a NOT gate can be made out of a single transistor. All right, so I hope that wasn't too complicated. I mean, I don't expect you to understand the physics of how transistors work. I just tell you that you can build these little electronic devices. Basically, they are made out of silicon, which is a material, and by putting arsenic and gallium and other materials into the silicon in a very special way, you can actually build a device that does this. Okay, and so there you go. There's a transistor. All right. Now, so what? I mean, I've done the NOT gate, but we also need to do the we've got 4 of them. We've got the NOT gate, which is a single transistor. Okay, but what about the OR gate? Well, unfortunately, the OR and the AND gate, before I can build an OR gate, I have to build a previous gate, which is known as a NOR gate. Okay, and you go, whoa, now there's too many gates. It's okay, it's not that bad. A NOR gate is just the opposite of an OR gate. Okay, and what do I mean by that? Well, if you take a look at the truth table here, the way the NOR gate works is whenever you would have gotten a 0 as an answer for OR, you get a 1. And wherever you would have gotten a 1 for an answer, here, here, and there, you get a 0. Okay, so it's just the opposite of an OR gate. Okay, so take the truth table, and this part here that I'm highlighting, that part there and that part there, those are the answers. Okay, wherever in the OR you would have seen a 0, you replace it with a 1, and wherever you would have seen a 1, you replace it with a 0. Okay, so it's basically a NOT OR gate or a NOR gate. And you go, why are you confusing me? Why can't you just do the OR gate directly? And the reason is that it's easier to build a NOR gate than it is to build an OR gate. Okay, so I'm going to build the NOR gate first. It's not too bad. You'll see in a minute. Okay, it's not too bad. So over here, let me now switch to the NOR gate. All right, like that. So if you take a look at this and you say, well, what am I looking at? Basically what you're looking at, let me make it a little bit bigger, maybe a little bit bigger again. Okay, so I'm going to cut off the top piece here. It's the NOR gate, but there we go. Okay, so you can see there that it's 2 transistors that are in series. Now what does series mean? It means one transistor is daisy chained off of the other transistor. Okay, now remember what the electricity would like to do. Okay, what the electricity would like to do is let me see here, what the electricity would like to do is start down here, so I'll do that in blue. So kind of the analogy of water would start here with the ground and would like to flow this way through the first transistor, flow that way through the second transistor, and then out like that. Okay, so that's what it would like to do. All right, now it will do that provided that you don't apply any electricity at either input A or input B. Only if both A and B, inputs A and B, are zeros, will you get electricity coming out here like that. Okay, and so maybe I can summarize it down here. Let me see if I can build a little table down here. If both A and B are 0, like that, then you get a 1 coming out. So this is like input A, there's input B, and there's your output. Okay, all right, I think you can see that. Yeah, it's a little small, but it's good enough. Okay, now what happens if at input A, instead of a 0 here, I were to apply a 1? Let me do that in I don't know, a different color here. How about purple? Okay, so I apply a 1 there, like that. So instead of at input A, I have instead of a 0 at input A, I have a 1. Well, what does that 1 mean? And that 1 means that I'm actually applying electricity to that input. And remember what happens when you apply electricity? Basically, when you apply electricity at the input of a transistor, you cut off the flow. All right? It's kind of like squeezing, like that one. Think of that one as like applying pressure and squeezing the hose shut. Well, if that's the case, well then there's no flow here. Okay, so that squiggly purple line I just drew means that there's no flow there. And if there's no flow, well then you're not going to get any flow here. You're actually going to get a 0 there like that. Okay, so in this case, A is a 1, so I'm going to write that into my little table here. Okay, B is a 0, but it was sufficient for me to squeeze the hose shut at input A to get a 0 out like that. Okay, at this point you should realize that if you apply a 1 to either A or B, because it doesn't matter which one, you're going to cut off the flow. Okay, so whether you applied whether you applied a 1 to A or you applied the 1 to B, you would have cut off the flow. And so the other way around, if I did 0 here, okay, and a 1 there, I would still cut off the flow. And then if I apply a 1 to both of them, well then I'm cutting off the flow twice, and I would still get a 0. All right, now I'm squeezing that in a little bit there in the bottom, but basically the upshot is only if both A and B are 0. In other words, I don't apply electricity at A and I don't apply electricity at B, will I actually get a flow. Okay, if I apply electricity to either A or B or both, I get no flow. And I emphasize the word or there because you could see how the or logic is emerging. Okay, now it's technically a NOR. So let's go back to the table here. So at the table here, what you could see is, only if both input A and input B. So this is like input A here, which can either be a 0 or 1. And this is like input B, which can be either a 0 or a 1. Only if both A and B were 0 did you get any output. Okay, so only if you did not apply electricity to A and you did not apply electricity to B did you get a flow. If you applied electricity to A, which would be here, or you apply electricity to B, which would be there, or both, you get a 0. Okay, and so that's basically your NOR gate. Let's go back to the diagram one more time, and let me clean it up a bit for you. All right, let me clean this up. All right, let's get rid of everything. Take a look at that. Okay, so remember how transistors work. If you're not applying anything, they don't cut off the voltage. Only if you apply a voltage at the input do you cut off the flow through the transistor. Okay, so right now I'm not applying any voltage to A, I'm not applying any voltage to B, and there is a flow. Okay, if I were to apply voltage to either A or B or both, I would cut off the flow. And so, I'll do that again in purple here. If I were to, apply a voltage there, I cut that off and you get 0 there. Okay. Conversely, if I apply voltage there, I cut that off and then there's no flow like that. Or if I apply voltage to both of them, I doubly cut it off and I still get no flow. The only way you're going to get a flow is if you don't touch either A or B. In other words, you apply no voltage to A and you apply no voltage to B. And that's the only way you're going to get any kind of a flow. And if you analyze that logic carefully, which I have here, you'll see you only get a flow if both A and B are 0. That gives rise to NOR logic. Okay. Now, it might be a little bit confusing to you, but if I took this like that, and you say, how can you make that into OR logic? Well, it's easy to make it into OR logic. Basically, it becomes OR logic if I take in the answer here, if I change any one of the 1s to 0s and 0s to the 1s, this is your OR. Okay, so your NOR looks like this. All right, you get a 1 only if both are 0. And with the OR gate, you get a 1 in every case except if they're both 0. Okay, that's the only time you get a 0 like that. All right, so you say, well, how do I go from the NOR gate to the OR gate? How do you go from this one? Because I built a NOR gate, but I want an OR gate. How do you do that? Well, you know the NOT gate. So basically, you build a NOR gate, and then at the end of it, you put a NOT, and that changes your NOR into an OR. All right? And I agree this is a little bit pushing it a little bit, okay? But I just wanted you to see that you can build this out of hoses and valves, if you like, okay? And so, even the ancient Greeks that did have hoses and valves would have been able to build a computer if they had known about binary and had thought about arranging the pieces the way that I'm doing it now, okay? But they simply didn't have the mathematics behind it. They had like the raw technology, but not the pieces behind it. And that's why I don't think that computer technology is purely a part of the Industrial Revolution, because the Industrial Revolution did give us, all the wonderful machinery to build the precision of the computer. But the computer, the digital logic, is actually independent of its underlying hardware. Okay, and that's kind of interesting. So you could actually build a computer out of hoses and valves, if you like. Okay, so once again, two transistors together would give you a NOR gate, but then you add add a NOT gate, and that turns the NOR into an OR. So the NOT gate turns NOR into OR. Okay, all right. And you get the OR gate. Now, we're going to be doing next class a count about the number of transistors that are required, okay? But, right now we saw that for the NOR gate, it took 2 transistors. Okay, so for the NOR gate, it took 2 transistors. And to convert that into an OR gate, it took another transistor. And so you can conclude that an OR gate is made up of 3 transistors, okay? So with these 3 transistors, 3 switches, okay, you're able to build an OR gate. All right, the next one is the AND gate. And just like the NOR, we're going to build a NAND gate first. Okay, so what's an AND gate? It's the opposite of an AND gate. Okay, so how does AND work? Only if both of them are 1 do you get a 1. Well, otherwise you get a 0. With an AND gate, only if both are 1 do you get a 0. Otherwise you get a 1. Okay, so this is again just like AND, except in the answer, wherever you would have gotten a 1, you make it a 0. Wherever you would have gotten a 0, you make it into a 1. Okay, so how would you build such a device out of gates? Okay, so let me show you that. And over here, there we go. There's the NAND gate. And let me make that a little bit bigger for you. So zoom in and zoom in again. Okay, and let's follow the flow of electricity. And so over here in the NAND gate, let me use blue. This is your source right here, okay, of electrical pressure, if you like. And notice that it gets to this conjunction right here. So the electricity can actually flow 2 ways. It can either flow this way through one transistor, the one on the left, and then out, or it can flow this way through this transistor and then out. Okay, so there's 2 ways in which the electricity can flow out. Okay, and now if putting in the logic here, if you don't apply any voltage there, and you don't apply any voltage there, don't apply any electricity at A, don't apply any electricity at B, you get electricity coming out at the output. Okay, now what would happen if I did apply electricity at A but not B? So suppose here, instead of that, I do apply electricity there. Well, then what would happen is I would cut off that flow, and this flow would die right in there. That flow wouldn't occur, but you would still get an output. And the reason is that the water can now flow. It could just avoid A altogether. It'll just flow through B, and it'll still flow out. Okay, and so this time, if I just cut off A, but I don't cut off B, I still get flow. Okay, so you can see how this is different than before. Before, it was sufficient to cut off one or the other to get flow, but here I have to cut off both A and B to stop the flow. And you can see, how I emphasize the word and. Only if both are cut off, only if A and B are cut off do you get flow cut off. And so what happens is, if I cut off A, you cut off flow in the one transistor. If you cut off B, you cut off flow in the second transistor. And when both A and B are cut off, that's when you get no flow at all. Okay, and so by putting the 2 transistors in parallel This is called parallel rather than in series. You get this different behavior, and this different behavior is basically the different logic. It is NAND logic, okay? So here, remember 0 means you haven't cut off either one of them, okay? You're not applying electricity to A, you're not applying electricity to B, and you get flow. Well, suppose you apply electricity to A, but you don't apply electricity to B, you still get flow because it'll just go around A and it'll go through B. And what about the other way around? What if you cut off B, but you don't cut off A? Well, then it'll just circumvent B and it'll still come out. Only if you cut off both A and B by applying electricity to input A and applying electricity to input B do you cut off all electricity, okay, flowing out, okay? And so this is NAND logic, and you say, well, how do I get AND logic? So now you just use a NOT gate to turn NAND into AND. All right, and what does that mean? Well, imagine that I have the same table again, okay, like that. And now what I'm going to do is I'm going to turn this into AND. And that means that wherever I had a 1 here in the answer, I get a 0. So wherever the 1s are, you get a 0. And wherever there was a 0, you get a 1. Okay, and take a look there. That is exactly AND. Okay, notice that AND is 1 only if both inputs are 1. Okay, and so an AND gate can also be built with 3 transistors. The only thing is that you're building it with 3 transistors, but you're building it with 3 transistors in a different orientation, or a different the connection is different. Okay, for the OR gate, 2 of the transistors have to be in series. For the AND gate, 2 of the transistors have to be in parallel. Okay. By the way, you might actually have experienced this with Christmas lights. Okay. Now, Christmas lights are more than one light. There's a whole string of them. But Christmas lights can either be put together so that they're in series or in parallel. The parallel are better because the series one, if one of the light bulb burns out, the whole strand goes out. Okay, and that's that's like your NOR gate. One of them goes out, it pinches off the flow at one point, they all go out. And then you're in a world of pain because like which bulb burned out and you have to keep trying every single bulb, okay? So that's terrible. Series is terrible. Parallel is nice because it doesn't matter if one bulb burns out, the other ones are still on, okay? The only way to turn the whole strand off is they'd all have to burn out, and that's like your NAND gate, okay? So these are really simple devices, but basically I've built, now an OR gate out of 3 transistors. Well, let's go through them. I built a NOT gate out of 1 transistor. I built an OR gate out of 3 transistors. I've built an AND gate out of 3 transistors. And I'm going to skip the exclusive OR because I don't want to overwhelm you with this. I think I just want to give you kind of like an appreciation for how this works, okay? So with the exclusive OR, it's a little bit more complicated. You need 4 transistors to build an exclusive OR, okay? And we'll skip that. If you're really interested, this is all over YouTube. You could just say, you could Google for any of these things, or, search YouTube for any of these things. And there's a million videos on how to build AND gates, OR gates, exclusive OR gates out of transistors, because this stuff is taught in, like I said, every single Introduction to Computer Science course, okay? And so there you go. That's a little bit of an aside, but really where we were at, just to remind you, we were at reducing 2-bit addition to logic. And I said I need a machine that does exclusive OR, and I need a machine that does AND. And I've got them now, okay? And I'm able to build them out of these transistors, okay? But really what I want to do is ultimately I want to build a long adding machine, like a machine that does long addition, okay? And so we need one more thing before we can put that machine together. It's not that bad, but it's this. We need a 3-bit adder. Okay, why a 3-bit adder? Well, remember, whenever we're adding 2 bits, like, we've got long addition, you've got like, a number like 1101, and we're adding it to 1111 or something like that. You remember how you align them, and then you add them column by column, okay, just like you do in decimal. The first column, you just add 2 bits. But then when you get to the second column, you might get the carry. And you might get into the situation where you're adding 3 bits. So you might have like 1 plus 1 plus 1. And we don't have a design for that. We have a design for 1 plus 1 or 0 plus 1, where we add 2 bits, but we don't have a design where we add 3 bits. And so we need a 3-bit adder, okay? Now, it's not too bad, but it is a little bit hard to get your mind around. So let me describe the the logic first, and then I'll actually build it for you. Okay, we'll put it together. So in addition, you can always add two things together first before you add in the third thing. Okay, so if you got three things to add, you can add them pairwise. Okay, so if we add like 3 bits, like A, B, and D, and by the way, I called my third bit here D so that it's not confused with C, which I've been using for the carry. But remember, you can add up to 3 bits and you'll only get 2 bits out. Okay, even if you have the biggest possible number, which is 1 plus 1 plus 1, even if you're adding 3 ones, you only get 1 carry 1. Okay, so 3 bits are going in, A, B, and D, and 2 bits are coming out, the carry and the least significant figure. Okay, but this addition here, okay, I'm adding 3 bits, but what I can do is I can add 2 bits first and then add in the third one. Now, why would I want to do it that way? Because I have a machine that adds 2 bits. We just designed it. And so I don't have a machine that can do 3 bits, but I can build the 3-bit adder out of 2 2-bit adders. Okay, and let's see how that's done. Okay, first conceptually. So first I'm going to add A plus B. That's not the complete addition, but I'm going to add A plus B first. Now when I add A plus B, I'm going to get a least significant bit, which I'm going to call L1. And I need to put a little 1 there because I'm going to have another one in a minute. Okay, so this is out of the first addition. I get L1 for my least significant figure, and I get C1 for my carry. Okay, so A plus B is going to give me L1 carry C1. Okay, then I'm going to take that number, which I got from the first addition, and now I'm going to add in the D. Okay, so now I've got D plus, there's D there, plus the number that I got from the first addition, which is made up of 2 bits, L1 carry C1. Okay. Now, how do you do that? How do you do that? Well, what you do is you align them, right? You align the D with L1, okay? And you go D plus L1, so you do that first. Okay, so there's my D plus L1. And when I do that, I'm going to get a number L2 carry C2. Okay. And I'll give you an example of this if you're losing it in the abstraction. I'll give you an example of it. So, okay, so once again, you know, C1 and L1, they came from the first addition. Now I'm going to add in D. But what you do is you add the D to L1 first. So you go D plus L1, and that's going to give you a number L2 carry C2. And then you go, okay, well, I got my L2. That's part of your final answer. But I've got these 2 carries. What do I do with the 2 carries? You add them together. And so your final number is going to be the 2 carries added together, followed by L2, and there's your answer. You go, oh, that's terrible. I can't get my head around that. Okay, so I've got some examples. Okay, if you take a look here, suppose we're doing 1 plus 1 plus 1. Now what I've done here is I've aligned them. Okay, so the first thing I'm going to do is I'm going to do A plus B. Okay, so I'm going to do 1 plus 1. So 1 plus 1 is 0 carry 1. There it is. So there's my A plus B. I did that first. Well, there's still the D there. There's still the D. So I didn't touch that yet. All I did was I added A plus B, and I got 0 carry 1 like that. Okay, now what's that in terms of my C1 and L1? When I did that, I got A plus B, I got L1 carry C1. Well, L1, that's like your 0. Okay, that's the least significant figure from the first addition. And C1, that's like your 1. Okay, so that's what I meant by L1 and C1 above. When I add A and B, I'm actually going to get a least significant figure and a carry. Okay, and I call them L1 and C1 because they're for the first addition. All right, now I still got D, but what do? I don't add D to the carry. I add D to the least significant figure of the first addition. They're aligned. Okay, and so at this point I go, all right, I'm going to go L1, that's this number here, plus 1, that's D there, like that. So L1 plus D, that's 0 plus 1, 0 plus 1, and that's going to give me a number that looks like C2, L2, that's my second addition. And now what's that going to look like? Well, when I do 0 plus 1, I'm going to get 1 carry 0, okay? And so for my second addition, my least significant figure is 1, and my carry is 0, like that, okay? And now I've got 2 carries. I've got the carry from the first addition, which was 1. I've got the carry from the second addition, which was 0. And when I add them together, 1 plus 0 is 1, and that gives me the overall carry. Okay, so a lot of steps there, but that's how you do it. Okay, when we add these things in our mind is doing a lot of things behind the scenes that we're not always conscious of, but consciously making every step conscious, that's what's going on. Let me do another example so we can see exactly how this is going on. Let me do the example where we go 0 plus 1 plus 1. Okay, so the first step is to add A and B. Okay, so when I go 0 plus 1, I get 1 carry 0. Okay, and there they are. So 1 carry 0, L1 is 1, C1 is 0. All right, then I add in D. So I go 1 plus 1 is 0, carry 1. So, right, 1 plus 1 is 0, carry 1. Now I've got two carries. I've got a carry from the first addition, which is 0. I got a carry from the second addition, which is 1. So I add the two carries together. 0 plus 1 is 1, like that. Okay. You might wonder at this point, are you ever going to be in the situation where C1 and C2, where both of the carries are 1? And the answer is no. Never are you ever going to be in a situation. Go through all 8 possibilities. Okay, there are 8 possibilities because the first number has 2 possibilities, 0, 1. The second number, so right here, this could have been either a 0 or 1. That could have been either 0 or 1. That could be either a 0 or 1. So 2 times 2 times 2 is 8. So there's 8 possibilities. If you go through all 8 possibilities, you will never have a situation where both the carry from the first addition and the second addition are 1. Okay, either they'll both be 0, or one of them will be 0 and the other one will be 1, but they'll never both be 1. Okay, and so now that you could just see, by doing it, by going through it and seeing it. So to add C1 and C2 in the circuit that I'm going to design in a minute, all you need is an OR gate. You don't need anything else. Okay, and why is that? Well, because only if one or the other is a 1 do you get a carry. Otherwise, you don't get an overall carry. Okay, and so that's basically how you build a 3-bit adder. You build a 3-bit adder out of two 2-bit adders. Okay, so that might have been a bit abstract. Let me actually build it. Okay, so let's go back to our logic.ly site, and there it is there. Okay, and we already have one of the 2-bit adders up. Let me get rid of I can always put the light bulbs back. Let me just get rid of this for now. Okay, and move those labels aside. So, and turn them off right now. Okay, so now we actually have 3 switches. Why? Because there's 3 inputs. Where's my toggle switch? There it is. Okay, there we go. So we've actually got 3 switches. And let me label that 3rd switch there. That 3rd switch, I called it D, like that. Okay, so there's D. So those are the 3 inputs, A, B, and D. And the first thing I did is I added A and B together, and that's this part here. That's the 2-bit adder where I add A and B. Okay, remember the exclusive OR here, that's your least significant figure. And you say, well, now how do I add in D? Well, basically, I add in D to the least significant figure using another 2-bit adder. So what that means is that I'm going to need another AND gate over here, and I'm going to need another exclusive OR gate over here. I take D and I feed it to the exclusive OR like this, and I take the other least significant figure here. You know what? I want to do that on the bottom here. Let me get rid of that. Let me do it down to the bottom here like that, so I don't get too much crisscross like that. So basically, when I've aligned, after I get the first addition, I take the least significant figure from the first addition. In fact, we can label it. This one here, that is your L1. Like that. Remember what I did is I took L1 and I added it to D. Okay, so there it is, added it to D. And not only that, but I also took it and I got a carry out of that, like that. So I took the least significant figure and I got a carry. Okay. By the way, this top one, this top AND gate, that was your first carry, and so we can label that too. This was C1, like that. Okay. So that gives me this AND gate here. Gives me the carry from the first addition. This exclusive OR gives me the least significant figure from the second addition. Then I take D and I add it into the least significant figure like that, and I get a carry and I get a least significant figure out from the addition with D. That least significant figure, that is part of your answer. So I'm going to put a light bulb right here, and that least significant figure goes directly to that light bulb. But now I've got 2 carries. And what do? I add the 2 carries together, and I can add the 2 carries together with an OR gate, like that and like that. Okay, so you say, why an OR gate? Why can you add the 2 carries together with an OR gate? Again, because you'll never be in the situation where the 2 carries are where the two carries are both 1. Okay, now what's this gate here? That one there is giving me actually what I called in my notes. That's actually giving me, whoops, what did I just do there? Hold on. That's actually giving me L2, and L2 is equal to D plus L1, like that. Okay, and this one up here is giving me C2, which is the second carry from the addition of D plus L1, like that. Okay, so there you go. So this exclusive OR gate down here, that's giving me the least significant figure, the second least significant figure from the addition of D plus the first least significant figure, and this AND gate here is giving me the second carry, which is the result of adding D to the least significant figure from the first addition. I know it's a little bit of a brainful, but there it is. Okay, and then finally, you know, we add the two carries together, and we need to feed that to a light bulb. So there it is. And there we go. What do we have now? We have a 3-bit adder. Okay, let's go through all the possibilities. Right now I'm adding 0 plus 0 plus 0. Okay, so remember, these switches, they represent the inputs. Okay, so what's 0 plus 0 plus 0 equal to? And the light bulbs are the output. 0 plus 0 plus 0 is equal to least significant figure 0, carry 0. Okay, so this is basically the answer is 0, carry 0. What if I made A 1? So A is now 1. You can see that the switch for A has got the blue border around it. So A is 1, B is 0, and D is 0. Now I'm doing 1 plus 0 plus 0. So 1 plus 0 plus 0 is 0. And you can see here the light bulb, the least significant figure, is on. So 1 plus 0 plus 0 is 0, and the carry is off. 1 carry 0. All right, one more time. 1 plus 0 plus 0 is equal to 1 carry 0. All right. Now, it doesn't matter whether it's 1 plus 0 plus 0 or 0 plus 1 plus 0 or 0 plus 0 plus 0. As long as it's 1, 1 and 2 zeros, okay, you're going to get 1 carry 0. All right. And so let's do the last one. The last one is 0 plus 0 plus 1, and it's 1 carry 0. Okay, so we went through all the possibilities of 1 added to 2 zeros. No matter where the 1 is, no matter where the zeros are, you're going to have 1 carry 0. Let's do it again. So over here we have, now we're in the situation of 1 plus 0 plus 0, and you've got 1 carry 0. Now we've got 0 plus 1 plus 0, and you've got 1 carry 0. And now 0 plus 0 plus 1, you still get the answer 1 carry 0. All right. Great. Let's do 1 plus 1 plus 0. So 1 plus 1 plus 0. 1 plus 1 plus 0 is 0 carry 1. Okay. And the same thing. Doesn't matter the order. So it's either, as long as it's 2 1s and a 0, doesn't matter what the order is. So right now I have 1 plus 1 plus 0. We could do 1 plus 0 plus 1, and it's still 0 carry 1. And we could do 0 plus 1 plus 1, and it's 0 carry 1. The last possibility out of all 8 of them is 1 plus 1 plus 1, and 1 plus 1 plus 1 is 1 carry 1. Okay? Even if you couldn't get your head totally around this circuit, you could still see that it works. Okay? As long as you're adding the 3 bits, no matter what order you're adding them in, you're going to get the right answer. All right? And there you go. You now have a 3-bit adder. All right? And why did we need the 3-bit adder? So if you're getting tired, we're almost done. We're almost done, because the last thing we're going to do is long division. And let me remind you how I did long division, okay? So basically, suppose that I gave you an example, like, you know, in your previous assignment from last week. Suppose I gave you an example. I said, you know what, I want you to do 1101 plus 111, okay? Do that addition, do that binary addition. Well, what you would do is you would take the first number here, 1101, ignore the carries for a minute, okay? So 1101, and then underneath it, you would align 111 underneath it like that, okay? Now, when you start to do that, in fact, you know what? I'm going to redo the addition altogether. Okay, let me just redo it for you from scratch. Okay. Now, when you do this, you start off with the ones column, and you go 1 plus 1 is equal to, over here, 0 and then you have a carry of 1 like that. Okay. Now, what I want to do is, rather than complicating my circuit too much, my final circuit, rather than complicating it too much, I'm going to use only 3-bit adders. And you go, but the first column only has 2 bits. I know, but you know what I can do is I can always put in a fake carry. Okay, so over here, I can always say, you know what? I'm going to start off my addition with a carry from a previous column that doesn't exist, and I'm going to make that carry 0. Okay, that sounds a little weird. You go, why would you do that? So that every single column represents 3-bit addition. That's the only reason I'm doing it. And you know that, putting a 0 here like that doesn't change the answer. So this is just for convenience. You'll see why when I show you the circuit in a minute. Okay, so I'm going to start off with this initial carry of 0, and I'm going to go 0 plus 1 plus 1 is 0, carry 1. And that first column was a result of 3-bit addition. Do we have a machine to do 3-bit addition? Yes. What comes out of that machine? Okay, 3 numbers go in. 3 numbers go in. Here they are. 1, 2, 3. Those are the 3 switches you saw a minute ago at logic.ly. Okay, and 2 numbers come out. A least significant figure, which is part of the answer, and a carry. And where does the carry go? The carry goes into the next column. Okay, the carry goes into the next column. And now we have another 3-bit addition. Okay, and so we're going to go 1 plus 0 plus 1, and what's that equal to? That's equal to 0, the least significant figure, and then a carry. And the carry, where does it go? Into the next column. Okay, and now we have 1 plus 1 plus 1, another 3-bit addition, and we're going to get the answer 1, carry 1, like that. All right, and now we're in the last column. 1 plus 1 is 0, and there's a carry of 1, but you know what? I've run out of columns, and you can't go on forever. So there's always the possibility of your last carry being what's called an overflow. And over here, that's where I'm going to put the overflow, like that. Okay, so the overflow means it would have been a carry that I should have carried into another column, but I just don't have enough circuit to do that, and so I'm just going to throw that carry into, I'm just going to let that carry just dangle off the end of the addition. Okay, you'll see what I mean in a minute when I do the circuit. But there you go. So these were the carries up here. Okay, here's your answer over here. But there's another little piece in there, like right there, and this is what's known as the overflow. Okay, and the reason there's that overflow is just as I said, we as humans could always add another column, but for a machine, you would actually have to build it more and more and more. So you can't go on forever because the machine can't be infinitely extended. There's only so many columns that you're going to have. Okay, and there you go. That's how we did that. Now you say each column is 3-bit addition, and we have a machine to do 3-bit addition. Can we collect together those 3-bit adders and make a full adder? And the answer is yes. That's exactly the circuit that I'm going to show you, and that'll end the lecture. Okay, how many 3-bit adders are we going to need? Well, how many columns did we have? We had the first column here like that. That was one column, and we needed one 3-bit adder for that. Then there was a second column here. We're going to need a second 3-bit adder for that. And there's a third column here. There's our third 3-bit adder, and there's our fourth column. So we're going to need 4 3-bit adders for this. Also, they kind of cascade into one another, because when you do the first 3-bit addition, the carry flows into the second 3-bit adder. And then when you do that addition, the carry flows into the third 3-bit adder. And then when you do that addition, the carry flows into the last 3-bit adder. And so the 3-bit adders kind of cascade into one another. Okay. Now, before I throw that circuit at you, because it's going to have a lot of pieces to it, let me just give some names to each of these pieces here, like that. So if you take a look at this addition here like that, it has a structure to it. Okay, meaning that no matter how many pieces, no matter what your numbers are, your first and second number are, it has this structure right here. And so there it is. So I'm just going to name the pieces, because each of those pieces, each of those bits corresponds to a wire. Okay, so this A1 here, that corresponds to that bit right there. Okay, now I call it A1 because it could be either a 0 or a 1. In this case, it was a 1, but there's a bit in that position there. This bit is that initial carry, which is 0. Okay, so the first carry is 0 by otherwise it doesn't work. Okay, so there we go. There's the first carry. That's that carry right there. There's the first bit of the first number. So the first number I'm going to call A, and there's the first bit of the first number, I'm going to call that A1. Okay, there's the first bit of the second number, I'm going to call it B1. So the first bit of the second number is B1. Okay, and then there's going to be a carry from that addition, there it is, and I'm going to call that C1. There's also a least significant figure from that addition, I'm going to call it L1, like that. So there's L1, and there's C1. And then there's the second bit of the first number, and I'll call that A2, and there's the second bit of the second number, I'll call that B2. And when I add that together with the carry from the first addition, I'm going to get L2, and that's going to have a carry C2 up here. There it is there. Okay, and then I'm going to add C2, A3, and B3. Okay, again, A3 is the third bit of the first number, and B3 is the third bit of the second number, and so on. Okay, so basically, A represents 4 bits of the first number, like that. Okay, and B represents 4 bits of the second number, where B1 is the first bit, B2 is the second bit, B3 is the third bit, and so on. I think you can see how I'm labeling this. Okay, and now let me go through how you do the addition. You start off with the first column, so you do 0 plus A1 plus B1. So you do 0 plus A1 plus B1, and what do you get? You get 2 things out. You get L1 carry C1. All right, and then you take that C1 and you bring it into the second column, and you do C1 plus A2 plus B2, and what are you going to get? L2 carry C2. Okay, now you take that C2 from the second column and you bring it into the third column, and you do C2 plus A3 plus B3. That's going to equal L3 plus C3, like that. Take that C3 into the fourth column. C3 plus A4 plus B4 is going to equal L4 plus C4. And then finally, this bit right here is the overflow, like that, right here, sorry. Okay, in that addition there. And the overflow is simply your last carry, in our case C4, like that. Okay, and there you go. So I don't think I need to go through this this verbiage here. Let me now show you a circuit that does that. I can't do this in logic delta ly because it would be too big. Okay, let me do it in yet another program. It's called TK gate, and it's used actually. Let me bring it up first. Where is it? Oh, there it is. Okay. Okay. So what you're seeing right now is a 2-bit adder in TK gate. TK gate is actually was a program that was written by a professor at Carnegie Mellon, and I actually wrote to him because I designed some circuits and I gave them to him using his program, and he incorporated them into the program, which is kind of cool. So it's used for very serious circuit design. So what you're seeing right now on your screen is basically your 2-bit adder. Okay, so where's the 2-bit adder? Well, this piece right here that's highlighted, let me see, yeah, that shows up. That piece right there that's highlighted, there's your exclusive OR. That gives you the least significant figure coming out. Okay, this piece here, which is your AND, okay, that gives you the carry, which gets brought out. And then there are 2 inputs, and these are the 2 inputs there. Okay, and the 2 inputs, both of them are fed to both the exclusive OR and the AND. So input 1 is which in my lecture notes I called A, is fed to the exclusive OR and to the AND, and similarly B is fed to the exclusive OR and the AND there, like that. So there's your 2-bit adder. Okay, now that 2-bit adder I'm going to represent as a box. So give me a second to, whoa, what did I just do? Okay, hold on here. There we go. That 2-bit adder I'm actually going to represent by this box right here. So what you're seeing there, that box, basically think of it as a 2-bit adder. In other words, inside of that box is the exclusive OR and the AND gate. Okay, now what I'm going to do is I'm going to feed the 2-bit adder with 2 inputs there, and I'm going to get 2 out. I'm going to get the least significant figure out there, like that. And you can see the highlighted wire, okay, on top, and then you're going to get a carry out like that. Okay, so again, you feed 2 numbers in, okay, and you get a least significant figure out and a carry out like that. Okay, now zoom out a bit. This is basically your 3-bit adder. Okay, what are you seeing here? What you do is you take the first two inputs like this, that one and that one. All right, you can see where my cursor is. Okay, and that's like your A and B, and you add them together into a 2-bit adder, and what do you get? You get a least significant figure and a carry. Okay, then you take your third number, there it is. Okay, and you add it to the least significant figure from the first addition, and you put that through a 2-bit adder, and you get out the final least significant figure. Okay, and then you've got these two carries, a carry from the first addition, okay, and you got a carry from the second addition, like that, and you feed them through the OR gate like that, and you get your overall carry. This is the circuit that I just built for you using logic.ly. You say, but it doesn't look like it, only because inside of these boxes here, those boxes represent 2-bit adders. Okay, and inside of the boxes are the AND and the exclusive OR gate. So each one of those boxes has an AND and an exclusive OR gate. Okay, they're basically two 2-bit adders. So two 2-bit adders plus this OR gate right here gives you a 3-bit adder. And now I can go up another level. Okay, and what you're looking at here is the final full adder. Okay, so how does it work? All right, so it's a little bit small, but let me walk you through it. This 3-bit adder, the one that's highlighted, okay, let me put my cursor over top of it. Okay, that's your first column right here. That's your first column. It's even labeled as your first column. And how does the first column work? Well, the first column takes A1. There's A1 right there. Okay, it adds it to B1. There's B1 right there. Okay, and remember there was that fake carry. There's the fake carry right there. Okay, that's basically a 0. That's a switch, just like the switches you saw with logic.ly, but they look a little different, but it's still a switch. It's still a toggle switch, and the switch is set to 0. Okay, so basically you're adding 0 plus A1 plus B1, and what do you get? You get your first least significant figure, and then you get a carry. And what do you do with that carry? You bring it into the second column, and the second column is also a 3-bit adder. And what does that 3-bit adder add? It adds the carry from the first addition. There it is, highlighted. Okay, there's the carry from the first addition, plus A2. Okay, there's A2, plus B2, like that. So C1, the carry from the first addition, plus A2 plus B2 will give you your overall least significant figure, L2, plus a carry, C2, which you bring into your third column. Okay, and now you've got C2, and you add to it A3, okay, and B3. So C2 plus A3 plus B3, what does that give you? That gives you the least significant figure that you write below the line, and then a carry, C3, which goes into your fourth column. Okay, and I don't have the fourth column labeled for some reason, but that's your fourth column. So you get C3 plus A4 and B4. A4 and B4 are basically, you know, the last digits of your first and second number, okay, plus the carry from the previous column, and that'll give you your least significant figure, and finally your overflow. Okay, and so you can see here that basically you've got 3-bit adder, 3-bit adder, 3-bit adder, and what's cascading between them is the carry. So the carry from the previous column is fed into the next column, and that's exactly how you add. So basically, I just looked at how I added my binary numbers, okay, how I did long addition. I had a machine to do 3-bit addition, so I said, well, every column is 3-bit addition, so every column has to have a 3-bit adder. And then I said, well, I take the carry from the previous column and feed it into the next column, and the least significant figure I just write below the line. So I just built a machine that does exactly what I do with my mind. And there you go, there's a mechanical mind, okay, designed. Finally, you want to see this thing in action. So here it is. Now, it's a little hard to see everything that's going on here. Let me just describe what we have. First, this box here in the middle, that is your full adder, okay? Now, what do you have to feed into that full adder? You have to feed it with the first number, the A number, and the A number is made up of A1, A2, A3, and A4. Okay, so the first number has 4 bits. The second number also has 4 bits. So that's your B1 there, B2, B3, and B4. So you actually have to feed 8 bits into the adder in order to add two 4-bit numbers. Your first number is 4 bits, your second number is 4 bits for a total of 8 bits. Okay, now we're going to set those using the switches here. So the top set of switches you see there, 4 in a row, those are your 4 bits for A. And then these other switches here, those are your 4 bits for B. Okay, and then on top of them you've got LEDs, so you can see the number in binary, so you know which switch is on and which switch is off. Okay, but I have also added these little LEDs here, and they basically will show the number in decimal. Okay, and that's just nice so you can see that it's actually working like a calculator. Okay, and finally, out on the other side of the adder, you get 5 bits coming out. Why? Well, because you get 4 bits for the answer, and then you get that overflow. Now, the overflow is part of the answer, but you know, if you want your answer, if you want to confine your the numbers that go in and the numbers that come out to 4 bits, unfortunately, you will have a 5th bit. If you add two 4-bit numbers, the answer will be 5 bits long. It can be 5 bits long, and that final 5th bit is what's called the overflow. It would have gone into, it's the carry that would have gone into another column, but we didn't have one. That's why I put it off a little bit to the side. Okay, so that's what you're looking at here. And inside of this box that's labeled full adder is the 3-bit adders, which cascade. And inside of the 3-bit adders is the two 2-bit adders and the OR gate. And inside the 2-bit adders is the exclusive OR and the AND gate. Okay, and so what you're seeing is kind of like turtles within turtles, or turtles on top of turtles on top of turtles. At the deepest level, you have the gates, and then I put together an AND and an OR gate to get a 2-bit adder, and then I put a 2-bit adders to create a 3-bit adder, and then I put 3-bit adders to create the full adder. Okay, let's demonstrate that it works. All right, so I'm going to turn on the simulation here and start it going. And it's cutting off the bottom slightly. Let me see if I can fix that. And can you see that? Yes, you can. Good. All right. So what you're seeing now is it's running, but right now what you're doing is the top number is 0, 0, 0, 0, the bottom number is 0, 0, 0, 0, and of course the answer is 0, 0, 0, 0 with an overflow of 0. Okay, let's do 1, 0, 0, 0. So sorry, we read from left to right, so this would be 0, 0, 0, 1. So the top number is 1. The bottom number is still 0, and of course when you add 1 plus 0 you get 1. All right, now let's do 1 plus 1. Okay, so right now all I'm doing is I'm toggling the switch there. So the top number is 0, 0, 0, 1. The bottom number is 0, 0, 0, 1. And when you add, you would do 1 plus 1 is 0, carry 1. And you can see here that your answer is 10, which in decimal is 2. So basically my little circuit is doing 1 plus 1 equals 2. Okay, well, let's do something more interesting. How about 3 plus 1? Well, 3 plus 1 is 4. Okay, you can see that it works. All right, what about 3 plus 3? Well, 3 plus 3 is 6. Internally, what the thing is doing is it's going 1 plus 1 is 0, carry 1. Then 1 plus 1 plus 1 is 1, carry 1. Then 1 plus 0 is 1. And then 0 plus 0 is 0, and you get the answer. Okay, so it's actually doing all the additions, including the zeros. You would have stopped after there were no more carries and no more digits. Okay, but this one will do it all of them because all the 3-bit adders are activated. Okay, so let's do another one. How about 7 plus 3? So 7 plus 3 is 10. You can see there it's giving. So this is actually decimal 10. And here's the binary. Okay, so 1, 1, 1 plus 1, 1 is equal to 1, 0, 1, 0. Okay, which is decimal 10. All right, let's do a few more since we've got this. How about 5 plus 3? 5 plus 3 is 8. Okay, how about 5 plus 7? 5 plus 7 is 12. What about 7 plus 7? So 7 plus 7 is 14. And you can see that it's working. Okay, what about 8? Let's do, whoops, here we go. 8 plus 3, I'm sorry, 8 plus 7. 8 plus 7 is 15. And that's as big as you can get with 4 bits. You can't count past 15 with 4 bits. So 1, 1, 1, 1 is 15. So if I had 8 plus 7, suppose I did 8 plus 8. 8 plus 8 is going to give me 16, and that's going to be bigger than you can fit into the 4 bits. In other words, you're going to overflow. So over here, if we do 8 plus 8, notice that my answer is 0, which seems strange, but it isn't. It's really 16. It's really 1, 0, 0, 0, 0. Now, computers, the way they're designed is they're designed, say, to work with only 4 bits. And so if you ever get into a situation, or the computer ever gets into a situation where the answer is 5 bits, that 5th bit is just thrown away. So it may seem strange to you that 8 plus 8 is equal to 0, but remember that there's the overflow bit that's thrown away. If you didn't throw away that overflow bit, you would get that 8 plus 8 is equal to 16. Okay, I purposely set up my LED here to just be off of the 4 bits that are part of the answer that the computer can retain, and throwing away the overflow bit. Okay, this is what's known as a 4-bit computer. Most computers are actually 64 bits, although there are some older 32 bits. That's going to become important earlier, which is why I wanted to show you that that there is this thing called an overflow. But you know what? Since we're here, let's just play with it a little bit more. How about we do 8 plus 6? So what's 8 plus 6? It's 14. Okay, and you can see that that worked. I don't know. What about 6 plus 5? 6 plus 5 is 11, and you can see that that worked. I don't know. 5 plus 3 is 8. Okay. And now 7 plus 5 is 12. And 7 plus 4 is 11. And I'm going to stop because I think you can see that this is just going to work for everything. Let me just do one more overflow. How about 15 plus 4? 15 plus 4 is equal to 3? Not quite. 15 plus 4 is equal to, this LED here indicates 16. So that's 16 plus 3. 16 plus 3 is 19. And indeed, 15 plus 4 is 19. So the answer, the adder is getting the answer correctly. It is getting 19. But if you only retain the 4 bits, which is all you can do in a real computer, you're throwing away that overflow and you're getting this weird answer of 3. Okay. By the way, this is what's known as modular arithmetic, and you do it all the time with time. Because if I said to you, what time is it 2 hours after 11 o'clock? Well, if you say 11 o'clock, 2 hours later is 1 o'clock. But what did you do? Well, you said, well, 11 plus 2 is 13. But then you threw away 12, that's your overflow, and you're left with 1. Okay, so think about if you're wondering what the computer is doing when it throws away the overflow, that's exactly what you're doing when you pass 12. Okay, you say it's 10 o'clock, 5 hours later. Well, it's going to be 3 o'clock. How did you get that? Well, 10 plus 5 is 15. But there's no 15 o'clock unless you're using military time. So subtract 12, throw away 12, which is your overflow. 15 minus 12 is 3, and it's 3 o'clock. Okay, that's exactly what's happening here. But instead, the overflow now is at 16, not at 12, like we have with our clocks. Okay, so there we go. That's the end of this lecture. And let me just quickly summarize what we did here. I showed you binary logic, first in terms of just logic in terms of sentences, and then I showed you how that worked in terms of ones and zeros, and I showed you how the binary operators and, or, exclusive or, and not worked. Okay. Then I turned to arithmetic, and I showed you how 2-bit addition is actually and an exclusive or. Okay, and then I said I can build a machine that does and I can build a machine that does or, and I can build a machine that does exclusive or and not. And I showed you how to build a machine that does and in terms of transistors, okay, which basically cut off the flow. So if you apply voltage, if you apply electricity, it cuts off the flow and there's no electricity that comes out. And if you don't apply electricity comes out through the flow. And so like just a single transistor turns a 1 into a 0 and a 0 into 1. Okay, and by hooking them up in the right way, you could build and gates, or gates. I didn't show you the exclusive or just because I didn't want to overwhelm you. Okay, but you could build an exclusive or gate as well. And that means that you can use transistors to build a 2-bit adder. Then I said, well, but we need a 3-bit adder to do long addition. So I showed you how to take two 2-bit adders and put them together to make a 3-bit adder. Okay, and then I said, well, when we do long addition, we just line up the columns, and each column is a 3-bit adder where the carry cascades into the next one. So I built a machine that does that, and basically I built a an adding machine. Okay, and so I've accomplished what I set out to do, and that was to build a mechanical mind. Now, it's not a total, it doesn't do everything the human mind does, but it at least does addition. Okay, and it doesn't necessarily do addition the same way the human mind does it, because the human mind does it in terms of whatever dynamics is going up there, but it at least does a process that's the same as the human mind. And it's ultimately built out of switches. Okay, and switches have, those are the transistors. They're either on or off. Okay, they're either on or off, and so that's the ones and zeros. That's why it's binary. So the computer is made out of binary, and the binary, the thing that does the machinery that does the binary is the switches. And by hooking up switches in a clever way, you're basically able to create a machine that does addition. In the same way, you can build a machine that does multiplication, a machine that does division, a machine that does subtraction, and all the things that I showed you in the last lecture. Okay, and then you can build a machine that does even more complicated things and more complicated things. Okay, more complicated operations, and before you know it, you have a computer. Okay, now at this point, your brain is hurting. I'm sorry. This was a brainful. I do want you to have an appreciation of this. If you ask me, what is it that I'm going to be responsible for? Because I can barely get my head around this. I'm going to have a tutorial video after this, as I usually do. And in the tutorial video, what I'll do is I'll do some problems, and the problems will be very similar to the problems that you'll have on your assignment, and they'll also be very similar to the problems that you'll have on your test. Okay, and basically, I'm not going to hold you responsible for like anything more than a couple of gates. Okay, circuits with a couple of gates. Okay, binary logic is easy. The circuits can get overwhelming because you got gates with gates with gates, and before you know it, you lose it. Okay, but there's no reason why you can't use that program logic.ly, which just go to the website and start playing with it. And so we'll do some exercises like that in a little tutorial lecture, and that'll answer the question, what am I responsible for? I had to go a little bit further than I want to make you responsible for, just so you could see that it can be done. So think of this as kind of like, like you have art appreciation, this is computer appreciation. So you walk away from this course and you go, yeah, I can see how you can build a mechanical mind. It isn't magic. It's a machine. It's a machine, and it's a machine that does the same thing my mind does. And if you have that, then you're an educated person in the sense that you know the world that you live in. Okay. All right, everyone. Thank you for putting up with this. And I promise you future lectures will not be as demanding. Okay. Bye-bye.